All right, good morning. My name is Buck Nye, president of HC Nye Company. We appreciate you attending our last webinar for 2020. This one is on kitchen ventilation system design, presented by Jeremie White. Jeremie has 14 years experience in kitchen ventilation system design, codes, and applications. Jeremie joined us in September of 2020 this year, and we're very excited for him to present to you today. General format that we normally do, we're going to go through. If you have questions, there is down at the bottom of your screen, there's a Q&A button. You can click that and type your questions in. We will monitor throughout the presentation. If there's anything that needs to be brought to Jeremie's attention right away, we will do that. And otherwise, we'll just hold most of the questions towards the end. And without further ado, Jeremie White.
Thanks, Buck. Thanks everybody for joining me today. Hopefully we'll get through a lot of these slides pretty quickly, have some time, trying to get you guys at least 10, 15 minutes of Q&A time. Whatever I don't answer, I will send out an email. And then also just following up with an email with all the questions and answers that we go through today. My contact information is on the screen there. Again, Jeremie, that's my direct phone number, email. If you guys have any questions, concerns, please feel free. Just give me a call, shoot me an email. I'm here for you guys to help you with anything you need for the kitchen ventilation side of things. Like Buck said, I was actually with Captive Air for about 13 and a half years. And hopefully we can get some good information out of this for you guys. So typically when you guys are talking about kitchen ventilation systems, when you get into a kitchen itself, it's pretty hot, noisy, smelly, greasy, slippery. They're very uncomfortable environments. And typically for most restaurant owners or operators, they want to make it comfortable in the back of the line, but also doing that at a cost-effective and energy-wise situation. This slide, just typical energy use in a restaurant, overall building energy use, depending on if you have a quick service, your fast food, institutional, that kind of stuff. It will vary for your HVAC loads, and that's the ventilating, so your exhaust, that kind of stuff, and heating and cooling. For the HVAC plus heating and cooling, we make it fair as well. So as designers, installers, when you get a commercial kitchen ventilation system, a lot of people kind of push it off to the side for the kitchen consultants or equipment providers, that kind of stuff. Typically, you'll have two different kinds of design, whatever the kitchen guy does, and then on the MEP side, what you guys do for the rest of that design. The codes and standards that kind of dictate kitchen ventilation systems. NFPA 96 is the cap. Okay, what's going on here? Okay, I'm working on a sound issue, guys. I'm sorry if you can't hear me. Let's see what we can do here. Okay. Can I go from your screen? You guys hear me?
Jeremie, we can hear you. It's a little muffled. If you can just speak up, please. All right, thank you.
A little muffled? Okay, let me see. Is that a little bit better, Jim?
Just make sure you speak up. Thank you.
Okay, I'll definitely do that. Don't worry about the crazy guy in the office. He only got the computer. So for hood stuff, the UL listings that are required for your hoods would be UL 710 for the hood itself. 1046 is for your filters. UL 300 for your fire suppression. Control panel, usually it's UL 508A. Power of ventilators require UL 762. Those are listed, your listings for those pieces of equipment. Typically for designing, International Mechanical Code for the areas that I'm talking to for most of this area, I believe you guys are New Jersey, Philly, Pennsylvania, and Delaware. Most of the PA in Delaware is dictated by IMC 2015. I know New Jersey and Philadelphia, the city area, is IMC 2018. There's definitely some big variances between those two codes. The biggest one for kitchen ventilation stuff is clearance to combustibles. UL actually has a test for clearance to combustibles. That's a listed exclusion in 2018, but is not in 2015. So typically that's one of the bigger things that pops up is the clearance to combustible stuff. ASHRAE standards, these were developed through NFPA, UL, and IMC. A lot of the ASHRAE standards are listed in there. Typically UL, what you're looking at is a safety standard. So it's your bare minimums, CFMs. Typically in most environments for kitchens, you really don't want to be designing at the bare minimums.
Hey, Jeremy.
Yeah.
Just can you bear with me 1 second? I apologize to everyone.
Yep.
Cynthia Fowler has a question. I'm just checking to see if everybody can hear you.
Okay.
Cynthia, I just allowed you to talk. Can you hear him okay?
Yes, I can. I did not have a question.
Oh, okay.
I'm good.
My apologies. All right, thank you. Okay, Jeremy.
This is just a quick sheet of the different research projects that ASHRAE has done over the years, from 93 all the way to present. There's actually a couple new ones listed on there. I know the UV one just, I believe, was approved. They have one for dishwashing heat gain. And I believe Technical Committee 510, which is the kitchen ventilation research division of that. I believe their next one, what they're looking for is a kitchen ventilation design guide, which will definitely help going forward. Okay, good. So we need to kind of rethink our design approach. Typically what happens, like I said, was you have two different design approaches, which is the traditional, the kitchen guys do their side of things, and the MEP does their thing. And usually what happens is a lot of people will say, well, there's no way we can keep or comfortably keep that kitchen cool. And that's a false narrative. Big thing with this is we're able to keep server rooms cool and nice. How can we not treat our back of the house employees the same way? I mean, we treat computers better than we do your typical kitchen equipment staff. So like I said, your traditional design is it's an ancillary space. You're typically just doing heated makeup area. And then in some places, they're actually allowing untempered makeup air. And then, like I said, usually it's a food service designer, a consultant, someone on that side that deals with the equipment layout is specifying the hoods, and now they're starting to specify fans and makeup air. Whereas hopefully I can help you guys and make this more of it's mission critical. We want to heat and cool that makeup air. We need to make it a little bit more comfortable for the kitchen staff. And in the long run, it does help their bottom line, because a guy working down the street from a kitchen that's pretty comfortable to work in talks to a line cook down the street and says, hey, I'm unhappy here. I'd rather be nice and comfortable working there than. And then hopefully we're, like I said, moving forward, mechanical will be specifying these systems, because overall you guys have to control the overall building. And traditionally kitchens are energy hogs, but also ventilation hogs. So it's usually one of your bigger pieces of equipment for ventilation air. So going through today, what we're trying to do is we're going to optimize our hood selection, optimize the way that makeup air is introduced, talk about filtration, to get rid of those slippery, greasy floors, spaces, everywhere in the kitchen, and then touch on some demand control, ventilation, and some fire system stuff. When we do all these things together, the result is hopefully an integrated design with an overall positive building, and you do want to be negative in the kitchen space. So optimizing your hood exhaust rate. As we stated, commercial kitchens are notorious for high energy use. They're big on efficiency, but a lot of it is poor design. So we want to maximize that efficiency as best as we can. And your best bet for doing this is using a listed product. And depending on where you are in the US, a lot of jurisdictions require listed hoods, not all do. So when we're talking about hoods, there's a lot of different variations of hoods. And your hood selection is really going to be based on what kind of cooking equipment you have to cover. You want to use the best hood you can to cover that equipment appropriately. So like a back shelf hood's not going to be very good at covering a double stack convection oven. Those are typically meant for countertop kind of equipment. Those ovens are going to overhang that back shelf because typically a back shelf hood is narrower, a lot closer to the cooking equipment. A lot of places you'll see back shelf hoods are your fast food and quick service types of restaurants, Five Guys, McDonald's, Burger King, that kind of stuff. You see these a lot. Or you'll see the Passover hood as well. Don't see it as much with Passovers. Typically, for most institutional cooking restaurants, quick service, you'll see a wall mount, a back shelf, or an island configuration. So like I said, hood selection, your big thing there is what type of hood. That's the first thing we're going to do. We got to figure out, hey, what kind of cooking equipment we have, and then that's going to help us select the type of hood. Next would be the cooking ratings of those pieces of equipment. When you're sizing a hood, it's based on the heaviest duty appliance. So if you have a bunch of ovens and then a charbroiler, that hood has to be sized for heavy duty. Adequate overhangs, that's probably the biggest thing I see when I go out to see restaurants and they're complaining, hey, things aren't working properly. Usually they're pieces of equipment. They'll have a fryer hanging out of the hood. They have it all the way up to the front of the hood instead of pushing it back. They're kind of beating the edge of that oven versus actually having that fryer pushed back a little bit. So cooking equipment placement is also big. If you had that charbroiler at the end of the hood versus in the middle and ovens on the sides. And then we'll talk about some end panels as well. So cooking equipment classifications. This is a list I took from IMC. There's similar ones in ASHRAE, the handbook, and also some of the other ASHRAE standards as well. Like I said, when you're sizing a hood CFM, it's based on the heavy duty, or the appliance with the heaviest duty rating. So, I mean, you could have, like I said, nothing but ovens, and then you have an open burn range. Ovens and a broiler, it would be a heavy duty hood. So how do hoods work? Heat rises. Typically when you're cooking, you're releasing convective heat, which smoke, your effluent, your grease particles, that kind of stuff is going up into the hood. And then also we're trying to exhaust as much radiant heat as we possibly can. You're not going to get all the radiant heat, so there is some radiant heat gain. And there were some, I believe, a couple of ASHRAE standards in that previous slide that went over different heat gains to space. They've done it, I think, in the 90s, and they did it in the 2000s, just because of changes of appliances technology, getting appliances that are giving off a higher heat load. So it's a lot different than it was 10, 15 years ago. And then that effluent, when it heats, it rises, it fills, that expands. So through research project 1376, this was taken from the Food Service Technology Lab in California. They've done a lot of third-party testing on listed hoods, unlisted hoods. They do a lot of stuff with ASHRAE in conjunction. And they wanted to see, versus there you have an oven that's running pretty much full tilt. And if you're looking at it, you're not seeing any smoke, that kind of stuff. So you're assuming, hey, the hood's doing its job, it's capturing that heat, that convective load, it's doing what it needs to do. But using an infrared camera, basically, you're seeing that heat load slightly spilling out right in front of this hood here. So in reality, this would pass a smoke test typically out in the field, but you're adding a different load to that space. So you would be, in reality, failing a capture. So the big thing with a listed hood, and a lot of the manufacturers do this, is they have some sort of means to circulate that effluent in the hood and that capture volume. As you see, typically what happens is that hot, buoyant air is going to cling to that cooler surface in the back, go up to the filters, and be sucked out. But not all of it's going to be sucked out on the first go through. So it has a tendency to circle back. A lot of people will use I believe it's a capture baffle for some manufacturers. I've heard it's called a magic triangle. Some companies also use little fans that kind of push the air in. They all accomplish the same thing, is we want to recirculate that so it goes and gets sucked back out. here is actually a video that I'm going to show you where this hood is not capturing appropriately, and you'll see the kind of smoke rolling out. And then they come and place in panels. Let's see if they're rolling out there. Just by placing some panels, we've taken a hood that was failing and adding that extra radiant load to the space, made it a robust design that's capturing that radiant load that was lost to space that would have been put to the HVAC, returns, putting extra load, making these kitchen equipment guys that are your cooks, your line cooks, very uncomfortable, hot, complaining. And with end panels, it's a lot of people were saying, well, you have to go with a full end panel. You're not going to be able to see down the lines. A lot of people like to, for the cooks, see what's going on. Typically, for most end panels, it doesn't matter what kind of end panel you have. You can have quarter end panels, like shown on this back shelf hood here. These are not full end panels. I've seen them where you can use totally full end panels. The main concept here is by adding those panels, we're reducing the exhaust rate needed and lowering that energy cost, lowering or making that ductwork smaller, making that makeup air requirement less as well. So you're improving the overall design with using less. As this was done at the Food Service Technology Lab, they tested, I think, over 8 or 9 different manufacturers with and without end panels. They used partial panels, full panels through the testing, but basically what they found was with panels, you were reducing your exhaust load by 30% typically.
Hey, Jeremy.
Yeah.
Why wouldn't you use end panels for all hoods to reduce the total airflow?
You should, as a design, we should be doing that. The only time I would say it's hard to do would be those double island canopy hoods or islands in general, because you got people running through back and forth, and then if you have an end panel away, you could technically run into something. But in reality, anytime you have a wall canopy hood, a back shelf hood, I mean, typically for most manufacturers, back shelf hoods, they are integrating end panels to begin with. But anytime you do a wall canopy hood, you should really be using end panels. So hopefully just seeing some of those things that you saw right now, we should really start integrating end panels pretty much for every kind of wall canopy design we do.
Great, thank you.
Another thing we talked about was overhang, side overhang and front overhang. Code requires minimally that you have 6 inches of overhang. And the way the code is written now is you're not being handicapped or you're not getting a penalty. The way the code used to be written in IMC was you took the total area. Well, when you did the total area, so if you made a deeper hood, you were being penalized by the exhaust rates that you would have to use. Now with the code, the way it reads, it's CFM per linear foot of hood. So we want to make those hoods deeper. The benefit of that is overhang is definitely going to help. You're going to have a bigger capture volume. You're also going to be able to push those pieces of equipment back as well. So this is just typically from a lot of manufacturers I've talked to, what they recommend for front overhang, side overhang, if we can possibly do it. So as we were talking about IMC, this is the minimum CFM requirements for a unlisted wall canopy, unlisted back shelf hood, depending on the cooking rating. So your light duty, medium, heavy, and then extra heavy duty would be your solid fuel, which is starting to be a little bit more prevalent in a lot of open kitchen designs. Similarly, this is a listed table. So for that 10-foot hood, let's say, like I said, that previous example where we had oven, charbroiler, oven. Heaviest duty appliance would be that charbroiler. You're looking at 4,000 CFM. For the listed hood, depending on what you're doing, if you have end panels, that charbroiler is kind of sitting right in the middle. Those ovens are on the back, or right side by side, kind of acting like end panels. You're probably a little bit closer to 230 to 240. So, I mean, that's 1,600 CFM savings just by going with a listed hood and some end panels. And then ASTM 1704 is actually a performance standard. They did that testing based on what the Food Surface Technology Lab did, in testing all those hoods with and without end panels, and using a listed hood, pushing that equipment back. And this is kind of an average of what they had. So you can see even then, typically 150 is the minimum UL listing for light duty equipment. A lot of manufacturers will not, you're not doing it at 150 or anywhere from 175 to 200 typically for a hood that's covered just a bunch of ovens. And exhaust rates, this is actually from ASHRAE standard 154. They actually only require listed hoods down, but this used to be in that publication, I think in 2011, prior to 2011, but also ASHRAE 90.1 has something similar, and 189.1. Typically, anything over, for 90.1, anything over 5,000 CFM, you have to abide by 3 requirements. At least 50% of that air has to be transfer air, demand ventilation on at least 75% of the exhaust rates, or you're using a listed recovery device. And then they want you to use lower CFM requirements. And the nice thing about this, if you take a look at these requirements that they have listed for a wall canopy hood, they're very similar to what you're seeing for the ASTM and listed products. So the reason why 154 doesn't have that chapter in it, or that table anymore in it, is because they want you to use a listed hood. The benefits there. This is a mixed flow, mixed equipment kind of configuration. Typically, that's what you're going to see in most commercial kitchens. You're not going to just have all ovens unless they're doing some prep stuff. 10-foot hood, fryer, broiler. You can do a range, griddle, and then an oven. It's pretty standard kind of concept for most restaurants. They did 8 different manufacturers and then a kind of a generic sheet metal hood. Tested the CFMs, used the Schlerin cameras, and basically ASHRAE 90.1, that's standard. What they're looking for is for heavy duties, 280 right across. So all your listed manufacturers are pretty much under that. The nice thing is if you're taking a look at this and you have a hood, it's grandfathered in, they're still having problems and they want to make it more efficient, just even adding panels to that generic non-listed hood improve the capture that much. So when we talk about overhang, again, the big thing is listed, the IMC requires only 6 inches of overhang. And as you can see, this is off of, I believe, a pizza oven. The heat, you can kind of see rising, kind of slowly and surely spilling out, adding that radiant load. Just adding some overhang onto that piece of equipment, you're improving capturing containment of that radiant heat load. Excuse me. So to kind of summarize what we went over on this portion of the presentation, for exhaust rates, your big thing you want to do is size that hood appropriate for the equipment you're covering, have the proper overhang. For wall canopy hoods, back shelf hoods, we really have to be utilizing end panels. And another thing that didn't talk too much about is pushing those appliances back. So like in that mixed flow, typically what happens, you'll have these fryers and stuff kind of push forward so that they're the same distance from or across, because they don't want to cooks and stuff like that, like to walk down the lines. The problem with that is typically what happens is you're going to get a lot of airflow that kind of comes in underneath the equipment and comes back, because that hood's basically a big vacuum sucking. So it's pulling from everywhere. So if we can seal off that back end there, it's going to improve your capture as well. So pushing appliances back is usually a pretty quick, easy way to solve some problems. Next thing we're going to talk about is makeup air, optimizing that, basically the way it's delivered into the kitchen and the hood environment. I'm sure people have seen different kinds of signs like this, pull hard. Even then, some places you go in, you can feel the difference, especially in the winter months. When you go into like a pizza place or something right now, you can pull on that door and it's pretty hard to open it up because they turn off their makeup air typically, and they have a negative balance in that space. IMC 508.1 requires that you bring in that makeup air within 10 degrees of the space. There are some exceptions. Makeup air that's part of the air conditioning system doesn't decrease comfort conditions. The big thing I would say with this is we really don't want to be designing for the exceptions for the makeup air. So makeup air, how and why? So any kind of air, it's just physics, air that you're removing from that kitchen space, it's going to pull from somewhere. It's, like I said, a big vacuum, it's sucking up. We're going to have to provide air somehow. Different ways that we can provide it is through transfer air. That's a big one. It's been around for a while, but it's not really pushed as hard as it should be. Displacement diffusers, floor or wall. Very similar to transfer air. It's when you do a lot of the testing labs actually kind of test diffusers of floor as kind of the transfer air. You get great results with this. The problem with using this displacement diffusers with floor wall, kitchen spaces are notorious busy, and they need, and valuable, that space is very valuable to those guys with their cooking equipment, so you can't just throw diffusers all over the place. Ceiling diffusers, 4-ways, slots, your perforated ceiling diffusers, and then the exhaust hoods with your integrated approaches. You'll have air curtains, front face, your back wall or back return, short circuit or internal comp, your perforated supply plenums, or any kind of combination with these and the other above mentioned. So just some quick Schlerin kind of pictures of what they did in the testing labs. With the 4-way, you can see here they're typically high throw discharge. What happens with that is when it hits that front face, it goes down, kind of creates a curtain, which is that cooler air is pulling that exhaust and effluent out of the hood, so then you're getting capture failures. Displacement diffusers, like we discussed about, nice lamellar linear flow, push that exhaust back in there, gets circled in, does what it's supposed to do. Internal comp, one of the poorer performers in this test. Actually, most of these pictures were taken from the peer test from California, 2003. They did this test in which they tested the effects of makeup air on hoods. Failure at 14%. Actually, ASHRAE 90.1 doesn't allow it to go over 10%. A lot of listed manufacturers are actually not even making internal comp hoods anymore. Air curtain was actually one of the poorer performers. You really have to, if you have one of these types of hoods, is that velocity coming down, you have to account for that, because what happens is it's going too fast. It's basically doing the same thing that we talked about before, that effluent kind of circles around. This is nice, cooler air. This is going to pull it out and then drop it right into the space. Front discharge hoods. Typically, the air on this one didn't really get the memo that it needed to go out into the space, turn 90 degrees, and go right back into it. Basically, you're putting pretty much 100% load onto the HVAC, depending on what kind of makeup air. If you're just doing an untempered unit, that's complete load. Winter months up in this way, let's say you're doing a direct fired heated unit. Those summer months, a lot of humidity stuck into those HVAC returns. Back return is actually one of the better performer ones in this test. Failure about 40 to 50%. Big thing with back returns is when you're designing these or working with them is PF Chang's actually is one of the accounts I used to work on a lot. They have they pretty much had a standard design with back returns, and we typically would have a lot of problems with the walks getting blown out with their pilots because that air velocity was so high. So we had to keep it at a certain point. So we were basically designing 40, 50, maybe 60% makeup air, and then the remaining we were kind of dotting around the space with like perforated diffusers or some other means to get that air into the space. What's standard kind of now for most manufacturers is a perforated supply plenum. Basically, when you're designing these types of systems, what you want to really watch is that velocity coming down of that air. We want to make sure we're anywhere from, I think, 140 to 150 feet per minute max right here. So that by the time it gets to the edge of this hood, you're right around 90 feet per minute. And then that air is kind of pushing down a little bit and then gets sucked back into space. There's a lot of CFD analysis on different reports. I didn't include in here because it's more manufacturer reports, not based on ASHRAE's, the research project testing. And here's an example from a manufacturer of basically their dedicated makeup air kind of approach of what they were doing. So in this typical design, what we're looking at is a hood system that makeup air is providing about 80% makeup, or 80% of the air. They're looking for about 20% of that transfer air coming in from the rooftop units. And in this design, they're actually using kind of a dual plenum configuration. So with their dual plenum configuration, they actually promoted a little bit better capture for this PSV, because typically anytime with a PSP design, you kind of have to minimize the width of the PSV. Once you start getting bigger PSPs, anything over like 14, 16, 18 inches, you're getting a lot more diffusion into the space versus it being captured back into the hood. So this kind of promoted kind of almost like a little bit of an air curtain. So that air would go down into this area, that makeup air would kind of hug, but then the exhaust hood would do its job and pull it in. So you'd have less diffusion. So typical design, like I said, what you usually see out in the wild here for most. I'll be a big offender of this too. I did a lot of designs this way. So usually the problems that you have with any of these kinds of designs is your kitchen return air is pretty bad, especially if we're diffusing a lot of that nasty air that's supposed to be captured by the hood and it's getting thrown out into space. So with these returns, I mean, a lot of these could be a pretty hefty size. And then that outside air that RTU is sized for, because we're adding that extra load, it's not typically accounted for. So you're getting kind of a cycling effect of, hey, our system's not working. We're going to try to put more exhaust more, or bring in more makeup air. And usually the problem there is not that. It's usually we can improve your exhaust hood by doing a couple of things here or there. But looking at that and say, hey, was this rooftop unit sized appropriately for that space? Where was this return located? And if you have a return within 10 feet of the hood, it's definitely going to be a problem. And then dishwashers are really notorious. They're a lot of times you'll see the dishwashers will have little, we'll say eyebrow hoods, kind of based on the manufacturer. A lot of those conveyor type things really need to have that expansive hood that covers. With dishwashers, it's not a big thing because typically the type 2 hoods, it's about 100 CFM per foot. Just having a little bit extra coverage, it's the same concept as the ovens. Getting that larger side coverage is going to help with that plume that you typically get off of those dishwashers. So it's captured appropriately and sucked right on back out versus trying to account for all this extra latent load that you can kind of see in this picture. So ASHRAE actually set out and did a report on thermal comfort actually for kitchen environments, basically from October 2010 to October 2011. And they did a quick service, your institutional, your casual, kind of went over all of that stuff. And as you can see from here, the 24, that red line is 75 degrees, the blue line is 72 degrees. Didn't matter what environment, what zone. You can see from here, most kitchen environments, everyone's saying they're pretty warm or uncomfortable. So kind of summarizing from that 180-page report, the worst areas were typically right there by the cooking equipment where you're seeing close to 100 degrees. Warm kitchens throughout the year. And then your workers typically would become accustomed to that. And they really shouldn't have to be accustomed to that kind of that heat load that they're getting from those appliances. So how can we kind of work on that and make it a little bit more comfortable environment for those employees? This I took actually from the the ASHRAE handbook, maximizing on transfer air. So really looking at 90.1, using about 50% of that air, designing. You have the rest of the kitchen and the dining space that you guys are worrying about. Utilize that because you're already heating and cooling that air. Bring in a little bit more outside air for that. Use that transfer air, and then also sizing up an outside air unit for the makeup air. So kind of condensing and saying, hey, we don't need a dedicated makeup air unit. We don't need a rooftop unit for that kitchen space as well. We can kind of condense that into one unit. And they'll be able to handle that. So, and minimize your ducts. I mean, now you don't have, for this example, no PSP, no makeup air duct coming in, just your exhaust duct, no returns, just the supply duct coming down. So what will this do? It's improving comfort. What's going on now too with more outside air being kind of required across the board. You're also getting a lot more humidity control. You're getting these units that are sized with bigger coils so they can drop that dew point down more, reheat the air if we need it, and less equipment on the space. So here's an example of the design we actually kind of worked on in Tennessee. This is a 23-foot hood. You're exhausting about 4,800 CFM, has a dedicated makeup air unit with heating and cooling, 8 tons, a rooftop unit for that kitchen space. And then your dining room has a couple of air handling units with remote condensing units. So for this design, you're looking around almost 10,000 total CFM of supply, 23 tons. So if we kind of changed this design around and see what we can do. For this one, we went with 2 dedicated outdoor air units. The one in the kitchen, doing about 50% of the outside air load required, just a 2,000 CFM, no return on that unit. Then the dining space, 4,000 with a little bit more than 50%, and returns moved away from the hood as far as we possibly could. Also opened up the kitchen a little bit here. Used some perforated supply plenums to bring in that makeup air. So it's nice laminar kind of flow, using transfer air to its fullest here. So we're able to actually reduce the exhaust CFM from the previous design. We're replacing instead of having 4 units, going down to 2, eliminating that PSP. The extra for that design actually had the makeup air plenum in front, the dual kind of plenum configuration. So we're reducing a lot of the exhaust duct, or a lot of ductwork, and giving you a little bit more tonnage, a little bit less CFM as well. So what about costs? That's typically when people start hearing dedicated outdoor air units. They're like, oh, this could be very costly. Installation is really the biggest key here, depending on where you are. For this example in Tennessee, the installation cost difference was right around 13 or 14,000 for the DOAS being a little bit cheaper to install. So once you added those numbers in, it came pretty close to being equivalent pricing. And then they actually did a study based on 2 designs for the DOAS versus your standard rooftop unit. Big thing here was the comfort. You didn't have as big of a swing in the kitchen space as well as the dining as you did with the your standard rooftop designs. Same study, this is basically your average equipment use per day. Big thing here with what was happening is you're getting a lot more cycling on your rooftop design versus the your DOAS design. So going into the next thing, filtration. Trying to capture as much as we can at the source is the easiest way to go about this. There's a few different research projects that went over this. The big thing here is we want to capture as much as we can at the source, so it's reducing the grease that's up on the hood or in the duct itself, reducing it on the roofs, and the fusible links for the fire suppression systems, because typically those would clog up, wouldn't work. Some more pictures showing basically maintenance is a huge thing. If people are not maintaining their systems, you're gonna have problems. Not a very fun job for that guy right there. So as I stated, ASHRAE's did a couple of different research projects on this. 745 was back in the 90s. 1375 was back in 2008. And the big thing there was the efficiencies of these pieces of equipment have gotten drastically that much better. So they're putting off a lot more effluent that we need to capture. And this is basically going over what types of effluent that you're getting off of there. Typically, most mechanical filters, you're looking at the green area and above. Vapor, you typically can't capture with a mechanical filter. So they actually came up with the ASTM F2519, which is a efficiency test for filters. Back in the 90s and early 2000s when I started doing this, I would see standard filters or cartridge filters and they would proclaim that they're 90-some-odd% efficient. They never dictated where that was on the graph. This is actually the test for ASHRAE, and they did it over a wide band of particulate. Your best filter for this would be kind of a two-stage filter. So you'd have a standard mechanical baffle, and then your second would be kind of like a porous bead media. And those typically would capture the most grease. Biggest thing with this is also, you're getting a better filter, you also have to account for the static pressure loss that you're gonna have with that fan. So improving that capture at the hood is going to resolve a lot of grease problems that you have in your hood with your duct. Big problems with the duct is a lot of times if those aren't being cleaned normally or on a proper maintenance level, you have fire issues. If you're talking about, let's say, a solid fuel application, grease heat kind of starts to build up on those, and it has a lower flash point than your typical grease does itself. I think grease heat's flash point's like 130 degrees, where grease is a little bit higher. I think it's like 2 something. So the more that we can clean these or capture that grease at those hoods, the better it is for your fire suppression as well. Next thing we're going to talk about real quick is some demand control ventilation. There's lots of different products on the market here, depending on if you're using infrared for the types of equipment, or you're using duct temperatures with smoke detection, kind of an optical sensor up in the front of the hood, or your standard just duct temperature, and then a room temperature stat as well.
Hey, Jeremy.
Yeah.
Just want to touch on a couple of questions before we get too far into it. Can you discuss recirc type with PSP supply? I think you may have hit that. What ratio of makeup air versus RTU air is recommended at split perforated plenum delivery? You want to hit those two real quick?
To kind of conform with 90.1, you really want to do 50% makeup air, and then the 50% for the remaining 50% through your rooftop units if you can. If not, I mean, you can design and make things work. There's also the, excuse me, depending on what kind of hood you have, you can wrap around those PVSPs on the sides of the hoods too, so that way you can get a little bit more makeup air at the hood. But a lot of studies have shown that if you add too much air near the hood, it actually degrades the performance. Your best performing hood typically is actually a hood that's an exhaust only hood.
Okay. Do the exhaust fans need to run when the Ansel system is discharging?
Yes, that code is required. Typically, if you had a fire and let's say no one was there, the control mechanism actually would kick on the exhaust fan and make sure that's running. Your makeup air is actually cut off. So per code, you have to have the fan running. For most jurisdictions, there's some weird ones here and there that I think the last time I had something like that was an Indian reservation in Arizona.
Okay.
For the most part, exhaust fan needs to run on this fire as well.
And one more before we get too far. On the slide with the kitchen RTUs, the slide noted return air to the kitchen RTU. The IMC states that kitchen exhaust cannot be recirculated. It does not say that only kitchen hood exhaust cannot be recirculated. Can general kitchen return / exhaust be recirculated to the kitchen?
It can, but typically what we've seen and what you can see in some of those pictures is if that hood system is not designed or it's not doing what it's supposed to be doing, you're going to end up with some grease particulate and stuff getting backing into that return. So if you're going to have a return in that space, we recommend, if you can, having it more than 15 feet away.
Okay.
You don't want it to be competing with the hood. So like if you're using a demand, because that actually plays into this. If you're using a demand control system, you're actually lowering, depending on what you're doing. Let's say it's a low peak or low time, what's going on. You're not doing a lot of cooking. That CFM on that exhaust fan is going down. So also your makeup air is going down. But that rooftop unit in that space, let's say it's kicking on and it's sucking. So you could have a return that's actually sucking a little bit harder than your hood at that time. So you could be pulling extra heat load from that hood, just depending on where those returns are spaced out.
Great, thank you.
Mm-hmm. So your typical system for demand control, you're looking to automatically adjust that exhaust and supply based on what's happening real-time cooking. So you have, depending on what kind of system, temp sensors, optic sensors, there's building system integration. Depending on where you're at in the US, a lot of utilities are actually giving rebates because these systems are running off of VFDs. Fan loss, physics tells you, hey, this is what's going to be. So the biggest thing here is when you're reducing that CFM, you're saving fan energy. And typically what happens when most people are like, my hood's not working, let me just increase the CFM. You're increasing that fan energy, which is also increasing your horsepower typically. So the solution always isn't, hey, let's just crank up the hood and maybe everything will work fine. Quick example of a chain restaurant down in Raleigh. This is real-time data with the temp sensors going on. This has a demand control system, and it's basically modulating the system based on the cook load going out throughout the whole time here. Fire suppression, kind of touch on this real quick. 5019 requires it. Any type of type 1 hood system has to have a fire suppression system. It has to be listed to UL 300 standards, automatically activate. You have to have some sort of manual means of operation. So a pull station located down the path of egress, appliance coverage, and then hood, unlimited duct. So I kind of touched a little bit on the design of end panels. I think if we were using end panels, this is a big thing why I say quarter end panels are great, but if you can utilize regular end panels, it's going to benefit you a lot more. Here's the edge of the hood right here. Fire system activates. You can see that wall is catching on fire. So by utilizing an end panel right there, that would actually keep that fire from expanding and hitting that sidewall. Typically when you're designing a hood system, I think right here is just about the 2-foot mark. If you're within 18 inches of a wall, really want to expand that hood. Because quanta and safety, I mean, you're going to see if you have a fire. And like I said, this is set up exactly like most restaurants you'll see is they'll start pushing equipment out when it really needs to be 6 inches over. Oh, same one here. ASHRAE journal from 2014 kind of did a 60 years kind of comprehensive review of what fire suppression systems have been doing. Not a ton has been evolving, but there are some system manufacturers now that are using a water-based system. Yes, water, kitchens, fires, I know that doesn't sound right, but they use the way they use it is a surfactant, so kind of a soapy material, and then the way they discharge the nozzles at the equipment. And it's UL 300 approved. So, but the biggest thing that they found in their research project on this was application and maintenance. Maintenance was the biggest thing that causes most problems. And it was either at the appliance itself or up in the duct was typically where you had most of your fire problems for your kitchen ventilation systems. So kind of summarizing what we talked about today, lowering your exhaust flow rates, critical, finding that balance between low exhaust and peak performance, optimizing your makeup air, how you introduce that makeup air into the space is very critical on how well your hood system is going to perform. Your hood is, I wouldn't say is the brain, but it's definitely an important part of it. Your fans are kind of the brain, I'd say, in your control system. Robust filtration. If we can capture as much grease at the source as we can, it's just going to promote a better and healthier environment in the kitchen itself, but also improve your duct the grease that's collecting up on the roof. Typically, there's a grease cup on most of the power ventilators. I ask most of the maintenance people that go out there, take a look at those. Those typically never get filled, and what happens is you get a rain or something like that, it fills up and you have grease all over the roof. So last couple of seconds here, GREASEMASTER's been around for a while. We do have a lot of products. Please feel free to give me a call about these. One of the newer things that we kind of have is I didn't touch on this in there, but a residential hood. So we are doing kind of a residential hood for those weird applications for like nursing homes and stuff like that, where you have kind of a communal kitchen. So we do have something on that as well. But different types of filters. We do grease duct as well. Outdoor air units, heated units. You're looking at direct fired, indirect, electric. Different kinds of diffusers, makeup airs. Anything you have that deals with the back of the house, we can definitely help you with that. With that, look forward to the 2021 webinars. If you get the newsletters, that will definitely be there. Contact Jim O'Donnell about the PDH. And like I said, here's my information. Please feel free to give me a call, shoot me an email, let me know. But let's open up to questions.
All right. So question from Kevin Angle. Is there any new technologies utilizing energy recovery of the exhaust air?
There is, in the States, you don't have too much going on, but I know Holton has something where they're doing kind of an energy recovery unit. It has not passed anything in the US that I know of. Typically what happens for most manufacturers, what they're doing is they'll put a recovery coil kind of behind the hood for like a wash system, and using that to reheat like your hot water heaters and that kind of stuff. That's the only thing that I've seen that's been listed and approved in the US. Canada, like I said, I know Holton has a heat recovery unit, I think, but I don't know too much on the Holton stuff. So
before we get into a couple of the other questions, I just wanted to let people understand. Jeremie can help and design your system from concept to drawings. So he has the ability to do that here in-house. I just wanted to touch on that and make sure everybody got that message. Next question from Brian Reese. Are there any IECC codes that apply to kitchen ventilation system operations?
not that I know of, but I can double check on that. A lot of the IEC stuff is equivalent to what 90.1 had in hash rate. Not all of it. I haven't dug into it completely, but I can definitely look that up and get back to you on it.
Okay. Christopher, yes, we can send you the slide deck. Jim O'Donnell will get that out to you after the presentation today.
Sorry to interrupt, Buck. We'll also get you a copy or a recording for this. And then the last thing I'll do is I'll type up the questions and we'll send those out as well too. All right, thank you.
Yep.
Again, I'm sorry. I'm just trying to get through this as much as there's 35 years of history that I'm trying to jam in here. So if you guys, like I said, have questions, fire away. Whatever I don't get to, I'll definitely get to you via an email. If you want, like I said, you feel free to give me a call too if you don't want to go through that.
Okay. From Neil Feldman, it seems most manufacturer equipment cuts do not list heat rejection, and we may have to refer back to ASHRAE recommendations. Any idea why this is usually not furnished from the manufacturer?
Great question. I've actually brought that up when I was at Caterpillar as well. Typically what you'll see is there's a certain point where you get down the design parameters. Actually, FSTC, I think they changed their name to Fishnick on the West Coast. They kind of have a 4-part design guide. They also have a few different webinars, and they've done a real good job of testing, and they've shown that at a certain point, you're going to have radiant load getting off into the space. And we just, even when I was at Caterpillar, I would tell engineers, hey, if you're sizing for heat gain, your best resource is actually that latest version of heat gain calcs in ASHRAE.
Okay. A while back, this is from Stephen Smeagol. A while back, Halton made a Venturi-style grease-rated balancing dampers for hoods. Do they work well, and do they collect grease at an unacceptable rate?
I remember seeing those, but I don't remember seeing any information or testing done on them. I mean, code tip technically says you're not supposed to have any kind of damper in a grease rated duct. But I have seen, I mean, a lot of manufacturers do manual dampers and different kinds of dampers when you're using multiple hoods on one exhaust fan. So it is there as long as you have the listing from the hood manufacturer for that. I don't remember seeing any testing on it. I mean, I can ask around and see if I can get some information, but I remember seeing that, but I don't know how efficient it was. I can't answer that.
Okay. Last question we have is, does the residential style hood include an integral fire suppression system? Is it UL 507 listed?
The hood can have a system. It's we can either do it piped, and it would be I think it's 507A, and so it is. You can either do it piped in the field, or we can do it in the factory, and it is 507A.
Okay. We have another one. Residential style hood. Is it comparable to Denler style hoods?
It's basically what we did was take our back shelf hood, and so it's a commercial style hood, and we've kind of narrowed it down to something about 2 foot wide. You can go from anywhere from 3 foot long up to 8 foot, and it has an integral fan built into it that's an ECM. But it's pretty similar to what you'll see with Denlar and GreenX fan, or their fire ready hood. Very similar.
Okay. We keep having questions rolling. So this one seems to be more of a comment from Desmond Baker. Most municipalities use IMC code and at time disregard ASTM, etc. It is difficulty to challenge since their law is by ordinance.
Well, I mean, IMC basically states that AHJ, or authority having jurisdiction, has the last say. Chicago was notorious for this. They actually didn't allow listed hoods until probably 2 or 3 years ago. So, I mean, it's not law, and so depending on who your inspector is, it can be hard. But a lot of them, if you show them the information, a lot of manufacturers will. Like if you have a question about a listing on a hood or something like that, where we can show them, hey, the clear combustible is usually the biggest thing I'd run into. We can show the listings to the inspector and say, hey, look, we were tested to this, approved by ETL. We can do this, and here's the results showing that. And I've done different things with different inspectors on that. Performance usually for most inspectors that I have is not a huge issue, but there are some areas where they're like, hey, I need to see the report, and most manufacturers should be able to provide you that.
Okay. Last one, unless somebody has some more questions. From Daniel Andresen. I probably missed it, but what is the typical turn down ratio for exhaust airflow in a demand control system?
Good question. This usually causes a lot of turmoil between people. If you look at certain, Blink is actually kind of the industry leader in this category. When I was at Captive Air, we actually did, we were one of Blink's bigger providers of systems before they developed their own energy kind of management system. Blink would typically always say you can do 50% turn down. Problem with this is usually what happens is if you're designing your hood system appropriately, so it's listed to the UL standards, or we're doing ASTM design kind of thing with end panels, that kind of stuff. You can't get as much turn down at that point because you'd actually be starting to get below the listed value of the hood. So you gotta look at that and say, okay, well, this is the minimum CFM, that's UL listed. Once you start going below that, you're not abiding by code. So there's kind of a game to play there to make sure you're meeting all those requirements. And I know 90.1 actually calls out, I think, 50% turn down for your exhaust. I mean, that's good if you have an unlisted hood. If you're using a listed product, though, it's hard because you're going to start getting below a certain point, and if you get below that point, you're not in compliance. So when I was at Captive, typically what they did a lot was would say 20% turn down. And they're really based on your system. So they started implementing kind of a startup service with their guys, and they would go out and base it on what kind of cooking equipment, what kind of stuff you're doing. So it was kind of more of a live, because every job is different, every application is different. You can't have a cookie cutter, so I can't say, hey, this is it. But from a factory standpoint, they were looking at 20 to 30% typically.
Great. Well, that's it for questions, unless somebody has anything else. We could stick around for another minute or two. Really appreciate you all taking the time out of your busy schedules and to join us with our webinar series. We plan on doing more in 2021. Jim will be sending out the topics. If there's a topic that you would like to know about, and we happen to have that type of product offering, please feel free to send suggestions. We hope you guys find this of value. You know, today was the biggest turnout that we had. We had 175 people on, and we really appreciate you guys supporting us and allowing us to support you. So with that said, we'll stick around for another minute or two, and we appreciate everyone joining us, and hope you have a Merry Christmas and Happy Holidays, and look forward to talking to you all in 2021. Jeremy, thank you very much.
No, thank you. Well, what's it here? All right, I'm good to go. Again, everyone, if you just have questions after the fact, my contact information is right there. Feel free to give me a ring or shoot me an email.
All right. Thank you, everyone. Appreciate it.
Thank you, everybody.